Now, when we looked at carbohydrates, we defined that there are typical features like chirality of carbohydrates, where we have asymmetric carbon atoms, which give particular properties to the individual carbohydrate. And let's look at it in a little bit more detail. We said that these carbohydrates can be mirror images of each other, and we looked at the glucose for that. And we can also define something that is called an D and L designation, which is based on the orientation of the hydroxide ion, of the hydroxide group, I should say, on the last chiral carbon. That's the furthest away from the carbonyl group, with the highest number when we count the chiral carbon atoms in the Fischer projection. And the D isomer, where the D stands for dexter, dexter means pointing towards the right side, that's D. And we can have the L isomer. L stands for Lewis, which is the left side of the molecule. We can identify whether, for example, a glucose molecule is D or in the L form. So how do we do that? So here we've got our glucose molecule again, and with the mirror image. So here we've got 1, 2, 3, 4, 5, 6. Now the 6 carbon here is not symmetrical. It's not chiral, because we've got 2 hydrogens here. So it's not chiral. We don't need to worry about that. And the last chiral carbon is actually this one here, carbon 5. And what we see in this case is that the OH group points to the left, to the right, I should say. So the OH group points to the right, and therefore this would be D-glucose, D to the right. Whereas in this case here, we still have the carbon 5 as the last chiral carbon, and the OH group is pointing towards the left here, and therefore we've got the L-glucose form. Both glucose forms have the same physical properties. They are, for example, sweet, they've got the same solubility and things like that. But the big difference is that only the D-glucose can be used, for example, as an energy source in biological systems, whereas the L-glucose form cannot be used. So although L-glucose is sweet, the body cannot use L-glucose. So they are chemically slightly different from each other, with the D form pointing in the different directions. They are enantiomers, because we said enantiomers differ at every chiral carbon in the way that they are pointing in different directions. We can also have what is called as epimers. Epimers differ in the configuration at only one chiral carbon, and this could be any of the chiral carbons that we are looking at. So, for example, if we look again at our glucose molecule, so here we've got glucose, and we can immediately see that this would be, when we look at the last chiral one, this would be D-glucose. So D-glucose. And when we look at, for example, this molecule here, we see it is also in the D form. So it's also pointing towards the right, so it would be a D. But what we see is that the OH group and carbon, so 1, 2, 3, 4, that the OH group on carbon 4 here is pointing to the left, whereas in glucose the same OH group is pointing to the right. So that it is a different molecule, very different molecule actually. It still has the same formula, but it is a very, very different molecule, even has a different name. It is D-galactose. So a very, very different molecule. It only differs by the position out of one chiral carbon with the OH group, but it's a totally different molecule, and it is called an epimer. We can also have what is known as an anomer, and anomers are the result of the reaction of the OH group with the carbonyl function. So remember, we've got COH, that would be the aldehyde function, and then we have an OH function, say in position 5, and this OH, this can basically attack the carbonyl C either from that side, or it can also attack it from the other side. And when we look at it, then we get this hemiacetal that we've discussed. So we would get something that we either have, here we've got O, we've got other groups, we've got here an H, and we either have an OH group sticking up, and that is here this carbon 1, or if the attack is from the other side, we have this structure, that is formed from this hemiacetal reaction. As I said, we've got the hemiacetal reaction, and they differ really just in the way the OH group at this carbon that used to be our aldehyde is orientated. So this C1 here, this is now called an anomeric carbon. And when we look at the Haworth projection, here is our glucose. It is totally D-glucose, so it would be D, and this one is also D. So when this OH group points downwards, then it is called alpha. If the OH group points upwards, then it is called beta glucose. And both forms can actually be converted into each other. In water, this conversion happens quite easily. This conversion is called rotation. Rotation. And the alpha and the beta form can convert into each other. So there is a mixture of alpha and beta and it depends on which one is more stable, but they can convert into each other because this form, for example here, the beta form can open up into the aldehyde, and then it can, the OH group in the 5 position here can then attack on the other side. So this mutar-rotation is a function of this hemiacetal function. So as I said, if it is down, it's alpha. If it is up, it's beta form that this glucose or other sugars can adopt. And of course, what we can do then is we can attach other residues here, for example. So that's why we then need to be careful what happens when we link different carbohydrates together.